All right, and then the other toolkit function that we can look at here is 1 over x squared. And we have most of the same thing, except here as x goes to infinity, or as x goes to 0, we have the limit of 1 over x squared is going to be infinity. So on this one, whether we come from the left or the right, it's going to go to that positive value, the positive infinity. So we can write that as one statement, and it means we can come from either side and we'll go to infinity. So this was kind of what we had before, where you come from the left and the right, and then you have this number or this well-defined number that the limit is the same. But here we're talking conceptually that now this 1 over x squared function increases without bound, no matter which direction we come from. So I can't emphasize it enough that infinity is not a number. It's the idea that we can increase without bound. And so, of course, we have all the other ones. As x goes to infinity or negative infinity, we're going to 0, just like we did with the first toolkit functions. And so these two things, where we're going to find that the reciprocal of x going to 0 is going to be a pretty useful tool to us, that we can make some fairly quick calculations of limits by using these facts. Okay, so we spent a lot of time a couple weeks ago looking at asymptotes and how they behaved. So let me just resurrect one of those problems that we had before of a rational function. And so if we look at how this behaves, we know that we're going to have 2 vertical asymptotes and 1 horizontal asymptote. And we know that because the denominator, that x minus 1 term, will give us a vertical asymptote at 1. That x plus 2 factor gives us a vertical asymptote at negative 2. And then y equals 1, since the degree of the numerator and the denominator are the same, we'll have some asymptotes here. So if we look at the intercepts then, so in other words, if I plug in a 0 for x, then I'll get y equals 1. There's my y asymptote. And then my x asymptotes, I set the function to equal to 0, and I solve for x. And so that numerator will tell us where the roots are. And so we have negative 1 and x equals 2 as the 2 roots. So this was all pretty much the stuff that we were doing with various functions. And so what I want to show now is just what we would do in terms of defining its behaviors. And so this is reusing some of these expressions that we had in limits. So as x goes to infinity, f at x equals 1. That's basically what our horizontal asymptote tells us. And then as x goes to 1 from the right side, we're going to go to negative infinity. And so we know how to do that. We stick in a number that's close to but not including 1. That's just a little bit above it. And we can see that in the numerator we have x plus 1 is going to be positive, x minus 2 is going to be negative, and then the 2 factors in the denominator are going to be positive, so we'll have the short-term behavior go to negative infinity. And then if we come from the other side, it goes to infinity. And then as we go to the asymptote of negative 2, if we come from the left, it goes to negative infinity. From the right, it goes to infinity. And then, of course, the last one that we have is that x goes to negative infinity, and we'll reach our asymptote of, or we'll get closer to our asymptote of 1. So if I were to draw all the lines in, we're going to go through our intercepts. That gives us a clue as to where we're going to be with these. But The limits we get the same way that we did before, where we reason, you know, are these ratios going to be positive or negative? Are the factors in them positive and negative? And then come up with some idea of what the limiting behavior is. So this is just you know, what we've done a few weeks ago, but instead of writing the notation about, and I even use that little arrow, as you perhaps recall, where, you know, x goes to infinity, then we say, you know, f at x goes to infinity. This is just a little bit more formally stated, but it's saying exactly the same thing.
And then negative infinity goes to 1.
Yes. And the one thing it doesn't tell you, you know, it tells you what the long-term behavior is, but it doesn't tell you, is it just a little bit under or a little bit over? Because from a mathematical standpoint, it doesn't really matter. You're getting arbitrarily close. And if we wanted to know which side we're going to be on, then we look at the function and try and understand its behavior. Certainly there are functions that will alternate from the above and below the line and get progressively closer to it. Okay, so let's go back to this concept where the limit of 1 over x is going to be 0 as x goes to infinity. So we can generalize this, that if we have 1 over x to the n, where n is any number that's greater than 1, it's going to go to 0. Okay, so we saw that with 1 over x, 1 over x squared, and so any other higher degree, 1 over x cubed, 1 over x to the fourth, all those things will go to 0. And so we can use that to evaluate limits. And you know, when we tried to find the long-term behavior of a rational function, the ratio of two polynomials, we were kind of doing that in an arm-waving fashion. We didn't really do that so rigorously. But now that we have this particular limit, this allows us to see it a lot more clearly. So the trick here is that we're going to take the highest degree in the polynomial, and so that's going to be x squared, and so we'll multiply both the numerator and the denominator by 1 over x squared. And so when we extend that out, what we're going to get is 3 plus 2 over x minus 1 over x squared, and then in the denominator we have 1 minus 1 over x minus 5 over x squared. So here we have an expression now that if we just look at the individual terms, we know very clearly where they're going to go. The numerator is going to go to 3 plus 0 plus 0. The denominator is going to go 1 minus 0 minus 0. And so remember that rule that we had when you have the same degree in the numerator and the denominator, it's the ratio of the leading terms that tells you where it's going to go. Here's a demonstration of why that's the case, because these other terms, the way we've transformed this function or restated the function, these other terms go to 0, while the leading term of the term that has the highest degree just goes to its coefficient. So we're just multiplying by 1, and of course, you know, x does not equal 0, but that's not really a factor when we're increasing x without bound. Okay, so then, you know, our limit is just plain and simple 3.
Why did you multiply by 1 over x squared?
So I can put it in a form where my polynomials evaluate. If I simply went and I thought, okay, let's try putting in a really, really big number in 3x squared plus 2x minus 1, we're just going to get a really, really big number. It's not going to tell us much, and it's not going to tell us how that goes in relationship to its denominator. But if I multiply it by 1, which is 1 over x squared over 1 over x squared, then I get a form of it that these limits that I've looked at before, specifically the limit as x goes to infinity of 1 over x, or 1 over x squared goes to 0, then these things drop out and we get this real nice expression that goes.
You're getting rid of the x squared in the leading term only. Right?
Exactly. And so here's one for you to try. Now this is an x squared term again, but I want you to calculate two two limits. And I'd like you to spend a little bit of time on this, just to think, okay, how do I get, what's my limit as I'm going to go to -3 from the right side? And what's my limit as x increases without bound? Okay, so this involves the examples that I've had in the last two slides. What do you think? Did you get it? What did you get? Yes. Negative infinity. Okay. So let's do that. So we'll look at that. You find that first by factoring, and so we get -3. You're right with negative infinity. Okay. X equals -3 is the vertical asymptote. Okay, because if you look at the factors now, I couldn't factor the top, the 2x² + 1, but I know no matter what value I have for x, that's always going to be 0 or positive. All right, well, it's not even going to be 0 because I have the +1. The denominator, when I factor it, as I go to -3 from the positive side, x - 3 is going to be positive, but x + 3 is going to be negative, right? I guess I'm saying you're right at negative infinity, but I'm getting infinity here. Because if we have that asymptote at x equals -3, so we're going to come in this direction from it. We know that the 2x² + 1 is going to be positive, right? And then this factor here, this x - 3, since x is always going to be a little bit greater than -3, is going to be actually negative. So you're right, it is going to be negative. Let me make a change there. How's that? Okay, so it's going to be a little bit less than -3, or a little bit greater than -3, so that's going to be negative. And then we have x negative, something a little less than -3 + 3, and this one's going to be positive. So we have a positive, positive, and a negative. So you're right. Yes.
So when you're trying to find the limit as x approaches like a number from either the left or right side, you first have to see if you can factor out the actual function first, and then find the vertical asymptote, and then...
The first thing we're going to do is we're going to look in there and say, is it continuous at that point? Because if it's continuous at that point, we're just going to plug it in. And if we plug in a -3, we get 9 - 9 is 0, so it's going to be division by 0, so it's not continuous. Then we have to look at what's the short-term behavior on it. Okay? So then you factor it, you try and figure out ways to say, what's the sign of the numerator, what's the sign of the denominator?
Okay.
All right? Yes?
I'm confused how you got negative infinity. You made the second step, but then you didn't do any equations to get the negative infinity.
Yeah. Look at this again, okay? So this is going to be essentially 3 terms. This one, when we're on this side of -3, is always going to be positive. This one's always going to be positive. It'll be a small number, but it's still going to be positive. Now this is -3, and this is approaching -3, so this is going to be negative. So this function is going to be negative as x gets closer.
So any number, you look at what any number would make it.
Yeah. Well, not any number, but numbers as we get progressively closer to -3 from the right side. Okay, so then we have our vertical asymptote. Now how about the next one?
I know you have to multiply by 1/x², I think, but I'm not sure how to do that exactly.
All right, so let's look at the technique that I used just above that, where I'm taking the 1/x² times in the numerator and then multiply the denominator by 1/x².
Do you have to factor this time, or no?
You just multiply on through, and so we get 2 + 1/x² over 1 minus 9/x², and so the 1/x² goes to 0, and the 9/x² goes to 0, so we're left with 2/1, which is just 2.
Now with this one, do we need to do that, because we already know what the horizontal asymptote is?
Well,
Or
but
are we doing something different?
well, we're doing it more formally now. Okay, you learned a rule of thumb before. Now we're showing why that's the case. Okay, and remember, I'll post these charts. I know some of you are probably not seeing all my really fine writing, but you can look at them online.
But wait, if you plug infinity into those x's, how do you get 2? I'm still stuck on the plugging in, or not plugging in.
Well, you understand what I'm doing here. I'm
Yeah.
multiplying by 1,
Mhm.
okay? So then when I go here, I have these functions, and remember what I said about limits? We can take sums of limits and we can take ratios of limits. So as x goes to infinity, 1 over x squared goes to 0. So I'm really, the limit as x goes to infinity of 2 is just 2.
Oh, so you're setting those both to 0, and that would be 0 1 equals 2.
Right. Okay, so that's the particular section that we just went over is 2.5. And if you look at the section, it's a little bit longer than what I've just talked about, but almost everything that it's talking about has to do with our discussion around functions before that. What are long-term and short-term behaviors around vertical and horizontal asymptotes? So other than to show you how you do this with a formal limit, I think all the concepts should be there. So make sure that you go through the section and read it, and make sure you're picking up all the little fine points, and it should look all very familiar, except the examples that they have with exponential functions and trigonometric functions. Just blow over that. You're going to return to that next semester. Okay, so I'm going to go into 2.6, and this should also look a little bit familiar because we're I think I've talked about this at least twice before, perhaps 3 times, where we're looking at rates of change and how what that really means, and we call it the derivative now. And so if we look at a function, say an arbitrary function where we have 2 values, now I'm going to use a and x because the point that I'm interested in is a. Okay, it has a certain value, and x I'm going to say is any other value. All right, so I have f at a and f at x as those 2 points on the curve. And so remember this thing about the secant line and the tangent line. The average rate of change as between a and x is going to be this difference quotient again, where we have f at x minus f at a over x minus a. All right, that should look pretty familiar at this point, where it's the slope of the secant line, which is the purple line, and it just tells you what your average rate of change is. The rate of change may actually be different as you go along in the function, but between a and x, it's actually that. So now I'm going to introduce what I used to call delta x. I'm going to call it h, just because h is just a little bit easier to write. It's more compact. And so h is going to be the difference between a and x. Okay, or the distance between a and x is h. And so if I make a substitution here, I can say that x now is just a plus h. Okay, so a is the point that I'm interested in. If I add h to it, I'll get to this other point x. And then my function is going to be f at a plus h. So these are the same things. So f at a plus h equals f at x, and x equals a plus h. So if I rewrite that difference quotient, I'll get f at a plus h minus f at a divided by h. Okay? So what I'm really interested in is what's the instantaneous rate of change now? Because the average rate of change is the secant line, but the tangent line that I have there is what I'm really interested in. And so what I'm going to do to figure out this instantaneous rate of change is I'm going to take the limit as h goes to 0. And you see what that does is as I bring h to 0, x is getting closer to a. And so if I look at the effect of that secant line, we're going to make that secant line closer to the tangent line. And so ultimately the limit of this thing is going to be that tangent line. And that's our instantaneous rate of change, which is what we're going to call a derivative. And so this was the formula that we ended the first day with. that looks so horrific, but perhaps now it looks a little bit more familiar. We're looking at something that starts from being the slope of the secant line, and as we take the limit of this thing as h goes to 0, we get the slope of the tangent line. Now the consequence of this is that it gives us an analytical way to calculate this. Now that you know how to calculate or how to figure limits, we can actually plug in some functions and figure out what the derivatives are at a certain point. Okay, so let's see if we can figure out what the derivative of this function x squared is, where f equals 1, or x equals 1. Yes.
Was it f prime a equals f a plus h minus f a?
There it is again.
Over.
Really?
I'm sorry.
Okay. You can catch that live on YouTube a little later this afternoon. Okay. So, anyway, so we have, this is the problem. We want to find what is the derivative where x equals 1. All right, so we look at what that's defined as. That's the limit as h goes to 0 of f at 1 plus h minus f at 1 over h. Okay, so this is just kind of the generic derivative formula, and instead of a, what I have is 1. So now I'll substitute the actual function in there. So I get 1 plus h squared minus 1 squared over h. And so this perhaps looks like a derivative, or it looks like a limit that you've calculated in the last few days. It should, because some of those exercises were specifically to be in this form. What we do here is we expand the 1 plus h squared, and then we notice that the 1 squared and the negative 1 squared is in there twice, so we can eliminate that. And we have 2h plus h squared over h. And here we have, we factor out the h, and so we just get plain old 2 plus h. And so as h goes to 0, our limit then is just plain old 2. And so we can say the derivative of this function at 1 is going to be 2. So the slope of the line tangent to that parabola of x squared, the line tangent at x equals 1, the slope is 2. Okay, so let's find the equation of the line now. Okay, the answer was 2.
How do you get 2 if it was 2 plus h?
Because as h goes to 0, 2 plus h is 2. Okay, so here's, I actually made a graph so we can visualize this now. All right, so here's that x squared, and I'm just looking at the positive numbers. I'm only interested in x is greater than 0. So at this point, 1, 1, that's the point that I want to find the derivative. And so that line looks like this. And so what we've done on the last slide was we calculated that the derivative at 1 is 2. That means the slope of that line is 2. Now what we want to do is find the equation to that line. And we'll find out a little bit in the next couple weeks why finding the equation of this line is interesting. The short story is it allows us to estimate values that are close to this point. So anyway, if you recall the point slope formula for a line, that should look really nice and familiar to you. We substitute in what we have for these values. So we know y sub 1 is going to be f at a. We know the slope m is going to be f prime at a, and then x1 of course is a. And so if I substitute in my my actual function that I'm interested in, x equals 1, and so I get this equation here, and I can then transform that into y equals 2x plus 1. I think I messed up on, oops, the equation here. So it's -2, this should be -1. How's that? Now they agree. Okay, everybody follow this line of reasoning? So we just use the formula for a line that we know, and we plug in the slope, which is the derivative we've calculated. F at A is y1, A is going to be x1. And so once we have the point and the slope, we can use the point-slope formula to calculate the equation. Okay, so I'd like you to try one. I want you to find the equation of the tangent line to the function square root of x, where x equals 1. Okay, so I want to make this substitution. Recognize that my slope is going to be the derivative at 1. And so if I make my substitutions, I get the limit as h goes to 0 over the of the square root of 1 plus h minus 1 over h. Now, what's the technique that I use to calculate this? Can somebody just say what do you, the conjugate, right, perfect. Okay, so then we're going to multiply this by the conjugate. All right, and we get this thing that looks like we're making it a lot worse than it really is. So when we expand the multiplication of that expression times its conjugate, it just squares the square root, so we get 1 plus h on for the first part, and then the second part it's minus 1. And then we have the 1 minus 1, so that's going to drop out, and we just get plain old h in the numerator, and notice we have a plain old h in the denominator too. So this will work out to be just what was the conjugate in the denominator left over, and that no longer goes to 0. This thing, as h goes to 0, becomes 1/2. So we know the slope of this line is 1/2. All right, we're only part of the way there. Now we recall what the point-slope formula is and make our substitutions. We know that m is going to be the derivative at 1, y is the function at 1, and x1 is just plain old 1. And so when I substitute in my values, I get y equals 1/2 x plus 1/2. Now, I know it's tricky to do, especially at first, and so, you know, it might seem a little awkward, but are you at least following the logic of it? Is it making sense from that standpoint? You're saying no? Where no?
Everywhere.
Okay, well, I have a couple more examples, and hopefully it'll start to clarify a little bit there. And if not, come see me in my office hours.
Could you maybe go a little bit slower and one of the next examples?
Yes. Okay. So let's just find the derivative. Actually, let me go back to the last one, and we'll do that one again. How's that? Okay, so we want to calculate the line. We have two problems here. We want to calculate the tangent, and we want to calculate the line, or the slope of the tangent. Okay, so here's our basic derivative formula. We're going to say the slope of this line is going to be the derivative at the point that we're interested in, and so we make the substitution. Are you with me here? Okay, so then what we'll do is multiply it by its conjugate. And we do this because that's our secret weapon in terms of eliminating these square roots, where we just can't, square the numerator and the denominator. That's not going to work for us. So we take it, we multiply it by the conjugate. And so then when we multiply by the conjugate, remember a plus b times a minus b is going to be a squared minus b squared. So we have that first term, that square root of 1 minus, or the square root of 1 plus h. So when that gets squared, we just get 1 plus h. Then it's going to be minus the square of the second term, which is just 1. And so we get 1 plus h minus 1. And then we didn't do anything with the conjugate in the numerator. We just left it there. Okay, so then what we do is we recognize that we have two things going on. And I'll write this out on the board in a little bit more detail. Okay, so this is where I'm starting from. And so my very next step that I didn't write on there is going to be just having h by itself. Okay, so all I did was I took 1 minus 1. And now I have h divided by h. And so that goes away and that becomes then just 1, like that. And so that's the step that, that I showed just before we actually calculated. Now as h goes to 0, this expression is just going to go to 1. And so we have the square root of 1 plus 1. So the square root of 1 is 1. 1 plus 1 is 2. 1 over 1/2. And that's how we get the that derivative.
And that is the slope?
That is the slope. And that's what the derivative means. We're using those words interchangeably. The derivative is the slope of the tangent line. Okay? Yes?
For the beginning, how come it's not, when you have f of 1 plus h, how'd you get from that to the square root of 1 plus h?
I've substituted in my function. My function is f at x equals the square root of x, and so f at 1 plus h is going to be the square root of 1 plus h.
Oh, okay. Oh, right. Okay.
Okay?
Yeah.
Yes?
So we're always doing the limit as h approaches 0?
Yes, and so we could do it by having two different variables in there. We have a and b, or x1 and x2, or something like that. It almost always is simpler if we just use h, because we're always just talking about the difference there between those two values on the secant line, but we're really only interested in one of the values. We're interested in as that, if I go back to this, we're really only interested in the slope at a, not at this x. Okay, so we want to make this h 0, so we want to bring it right down to 0. So what we're doing is we're drawing that second point closer to the first point.
So the 0 represents that there's not a distance between the 2 points.
Exactly. So imagine this animated. Your line is just going to go right up to your tangent line then.
Okay.
Okay, so then we'll go back a little bit here. Oops. And now we take the formula for the line that we have. Y minus y1 equals m times x minus x1. And so we'll substitute in what we know. And we get y minus 1 equals 1/2, which was the slope, and times x minus 1. So the 1 next to the y here is because f at 1 equals 1. This one here is 1 because that's what we're looking at. That's what our value of x is. And so then we basically simplify that and we get our equation. Okay, so the
What? I didn't get this equation, the equation.
Okay, you can pick up the rest of the notes from Moodle, okay?
1/2 x minus 1/2?
Yeah.
Thanks.
There it is again. Okay, so I'm not going to get all the way through this particular example. I just want to set it up. On Friday, we'll back up a little bit more. We'll do a couple more examples like I've just done, and then we're going to get into looking at the general case, and then we're going to look at the derivative as a function. So we're not just going to end up with a number, we're going to end up with a function that describes the derivative at any point x. Okay, so that's where we're going to go on Friday. But let's look at just if we had any old a and see how this works. And let's say we had this function, this is 1 over x squared, right? And so if I plug in my numbers and everything, what I get is this expression here that is just 1 over x squared with the values a plus h and a as x. And then one of the things that makes it a little bit easier is that if instead of writing the limit every time, I just don't want you to drop the limit because you're changing the meaning of what you're calculating. You can take that expression out and just do a simplification on its own, and that's what I'm doing here is I'm just saying, okay, let me hold this concept of the limit and I'll just take the expression that I'm trying to figure out because I want to simplify that. So I'm just starting again. So I copy over what I have, and I'm just starting with that expression down there. And then I basically combine the fractions, the ratios. And so, I know this is probably going to be too fast, but ultimately we get the same kind of thing where we can make the simplification work and get an expression that then turns into something a lot easier. And so this one, as we take it to 0, we get negative 2 over a cubed. And notice that this is for any arbitrary a, that you don't really always need a value. And in fact, we're going to have some rules that will make this a whole lot easier. So this will get generalized and it will get much easier. But for now, we do have to go through this exercise to really understand what's going on. Because we're calculating a slope. We're not calculating just an arbitrary function. This has a very particular definition.